Uh, Dear friends, let's start our today's seminar. Our speaker is Igor Mikhailovich Nikonov from the Moscow State University, and he's going to tell us about the crossoid structure on knots. Let's welcome.
Thank you very much for the opportunity to give a talk on this seminar. My talk is devoted to one structure which appears on coverings of crossings of knot diagrams. So we look at nodes combinatorially and consider nodes as equivalence classes of diagrams, where diagrams are just four-volume graphs with the structures of overcrossing and undercrossing in the vertices. And we also we consider these diagrams up to isotopy of such graphs embedded in the plane, or maybe any other oriented surface, and modular Ready-Master moves. So there are three Ready-Master moves, and they induce the equivalence between the diagrams, and the equivalence classes of diagrams are nodes and more generally links. And we will consider mostly oriented nodes and links, so we assume that each component of link or node, if we have only one component, is oriented. In this combinatorial approach, when we speak about invariance of nodes, we should construct, we should present a construction which gives an invariant value of given any node diagram. So if we have an invariant, in order to define this invariant combinatorially, we should take a diagram and somehow construct the invariant value. The invariance means here that if we consider two diagrams connected by a Ready-Master move, then the value of the invariant must be the same on the both diagrams. And a typical node invariance uses in this construction elements of the diagram. So given a diagram that is a four-line graph, we embed it in the surface or in the plane. We can consider the parts of this diagram, which are edges. We will call the edges semi-arcs. The vertices, that is the crossings, semi-arcs form arcs. We say that an arc is a part of the node between two undercrossings. And the diagram as a graph splits the surface into connected components, which are called regions. So to a node diagram, we may assign the set of arcs, the set of crossings, the set of regions, and we can use these sets in constructions of node invariance. And a typical node invariant looks as follows. Let us consider them the simplest node invariant, such as linking number. If we have a two-component link, that the number is just 1/2 of the sum of the signs of diagram crossings. So here we consider oriented link, and each crossing in this case locally looks as follows, or maybe we may have the following picture. When we look at the orientation of the node at the crossing. So the left picture is the positive crossing, and the right is the negative crossing. So we have positive and negative signs of each crossing, and we take the sum of these signs, but not for all crossings, but only for crossings where two different components intersect. So this will give us some integer number. It will be, in classical case, it will be an even number. So 1/2 of this number is the integer linking number of the link. And if you look at the formula, you see that the construction uses two types of invariant labels of crossings. And the first one is the sign of the crossing. So if we consider a sign that apply a ready-master move to a diagram, and if this move keeps the crossing, if the crossing survives after the move, then its sign will be the same. So this is an invariant label. And another label is the type, component type of the crossing. And we, for a two-component link, we have two types of crossings: self-crossings of one component and mixed crossings where two different components intersect. Two different components intersect. And we take the sum only for mixed crossings. So we use these labels to construct some number which is not a link invariant. In other cases, we may use covariance not of labels not of crossings but of other elements such as arcs. In this way, we may come to quandles and quandle invariants, such as the number of covariance and quandle cocycle invariants. We may also consider labels or covariance of regions, and we'll give we get in this way maybe shadow cocycle, so some invariants concerning three-bracket structure, Nebzhidovsky three-bracket structure of the node, and so on. So most of all combinatorial construction of invariants uses these invariant labels.
Igor, excuse me. In the last time, there is a very popular topic about motivic theory. Actually, there are many abstractions, abstract notions, for example, of S1, S3, and since we have abstract notions after Voevodsky of S1 and S3, so there should be abstract knots which can be defined, for example, over finite fields in algebraic geometry. So it would be great to understand what is a crossing, at least what is a crossing over finite fields. If we have a crossing, then we can dream further. Dream about Kaufman bracket, at least. Of course, we can do much more. So have you tried to think about that?
No, I have
you know, at one of our seminars, I don't know, remember which, there was a talk maybe by Frolov. I think you can watch the recording of his talk, and he was talking about something like motivic knots. So you see, motivic knot seems to be a very high level, so it should mean that all techniques we know from knot theory can be applied to some other parts of mathematics. And if we can, it would be really great.
Maybe. Maybe, but today I will not speak about these algebraic structures. So, but thank you for the remark. We in various construction of knot invariants, we use different invariant labels of crossings or arcs or regions, and the question one can consider is which types of labels, invariant labels, a crossing can have, or in an arc, which labels exist for crossings, for an arc, and and thus we come to the following picture. So among all invariant labels of, for example, of an arc, we can consider the universal invariant labels. So that any other invariant labels is just an image of some universal label by some maps, by some map between the set of universal labels and the set of invariant labels which are used in a not invariant construction. And if we look at the universal invariant labels, you see that one can define these universal labels as the not diagram elements themselves. So if we look at universal labels of arcs, then we should say that the universal labels is just the set of arcs for all diagrams, modulo some equivalence relations induced by Reidemaster moves.
One more thing. I think you may compare this with the talk by Thomas Fiedler at one of our seminars. So he was talking about some labels, but he was doing something like tangle valued cocycles. Well, he was doing something for Reidemaster moves. So crossings were getting some labels, but they were more complicated. Again, try to compare this with Friedman. Fiedler, excuse me, Fiedler.
Fiedler, yes. Okay. Okay. So when we define the universal labels, we consider diagram elements modulo equivalence relations induced by Reidemaster moves. So you can see in the picture above that if we consider a red arc in the left diagram, after one applies a second Reidemaster move, this arc splits into two arcs, and we should say that these two arcs on the right diagram must have the same label, invariant label, as the arc on the left. So we should identify all these arcs in one equivalence class, and then consider the set of these equivalence classes. So we get some set of arcs which will be assigned not to a concrete diagram, but to the knot itself. Sorry.
Let's go on. Let's go on. Is everything okay?
I'm sorry, there was an interruption. So I continue. So we consider these equivalence classes which are just assigned to a node, but not to a diagram. And we may say that the equivalence classes of arcs the set of all equivalence classes for X will be the X of the node, not of a concrete diagram. So we get to these sets of arcs, crossings, and regions of one node, not of diagram. So the question is how to describe these sets. They are defined combinatorially as some equivalence classes, but it appears that these sets admit topological description, namely, we may consider the following picture. Assume we have a node, consider it geometrically as an embedded a circle of several circles for a link in a thickened plane or sphere or other surface F. And then if we define the set of arcs of this node, we should consider the set of this red path which starts in the top boundary of the thickening and ends on the node. And we consider such path up to isotopy. So the isotopy classes of such path will be the set of arcs of the node. Analogously, if we consider the set of regions, and then we should consider path which starts on the top and ends in the bottom and don't intersect the node. So the set of isotopy classes of this path will be the set of regions of the node and so on. And for crossing, we should consider path which start on the top, ends on the bottom, and intersect the node twice. And the arc between two intersection point is framed. So we should consider the typical classes of such path with a framed arc in them. So this will be the universal labels for diagram elements. And if you see that we should deal with the isotopy classes of path considered up to isotopy, it is a very large set. So we can simplify our these sets by considering not isotopy but homotopy between the path. So we may consider homotopy classes of such a path which starts at the top of the thickening and ends on the node, and some other types of path. And so we get to homotopy classes of diagram elements. And it appears that these homotopy classes are closely related to some algebraic structures which appears on covariance of diagram elements. For example, if you look at homotopy classes of arcs from bottom to the node, considered up to homotopy, you get the geometric definition of quandle of the node. And other sets of homotopy classes leads to other structures. Arcs leads to quandle, semi-arcs leads to biquandloid. It is some structure related to biquandle. And today I am going to speak about crossings and the related structure which are called crossoid. Okay. So the structures are assigned to covariance of diagram elements. For example, when we consider quandle, we consider diagram and cover the arcs of diagram in some colors and assume there is some relations on these colors. And the relations, so let us consider the set of diagram elements, for example, arcs or regions or crossings, and assign some colors to these elements. So we color arcs, color crossings or regions, and we assume that there is some relation which allows to extend the coloring from one elements to other elements. For example, if we color regions of diagram, then we may assume that the colors of neighbor regions are connected by some function. So if we have an arc and a region on the left and region on the right, so the color of region on the right is expressed by a function applied to the color of the left region. This rule allows to color all regions of diagram when we know color of one region. And if you look which colors one may get from this rule, it appears that all these colors comes from Alexander numbering of regions. And so this rule will give Alexander number. Analogously, if we consider another rule which connects to colors of two arcs which are opposite at a crossing, if we have this rule from color C, we get color phi of C using some function phi. Then also we get some variant of Alexander numbering of the arcs in this case. And more complex propagation rules appears when one consider, for example, quantum structure or three bracket structure. For example, when Nabzhidovsky defined his three bracket, he used the following rule. We should consider currents of regions of a diagram and then apply the following rule. If we know the colors of three regions adjacent incident to a crossing, then the color of the fourth region is defined by the other three colors. This gives some function, some tree bracket, and one can use this tree bracket structure and write down the relations which appear from Rademaster moves and get the ternary quasi-group structure defined by Nabzhidovsky. Analogously, if one consider occurrence of semi-arcs and use the following rule that if we have if we know colors of two adjacent not opposite semi-arcs incident to one crossing, then the colors of the other two arcs are defined by these colors X and Y. This leads to the biquandle structure. And in the case when we consider currents of the crossings, we will use the following polygon rule. Assume we have some diagram, and consider a region of this diagram. we will assume that the color of one vertex of this one crossing incident to this region is determined by the colors of the other crossings. So if we have a region of a diagram and have, for example, an crossings incident to this region, then the color of one crossings is can be expressed through by some function through colors of the other crossings. So we will use the following rule and then write down which relations and should be imposed on this function f to so that the set of covariance which satisfy this polygon propagation rule for two diagrams connected by a radial move must be in a one-to-one relation. That is, there must be bijection between the covariance of crossings of two diagrams connected by a radial move. So will give us some structure, which I will call crossoid structure. So let us pass to the definition of this crossoid structure. So in general, we will consider covariance of arcs, semi-arcs, and crossings of diagram. So the crossoid structure consists of set of colors for crossings, C, and colors for semi-arcs, A. And then we assume that these colors for crossings contains the information on the sign of the crossing. So we have the sign function on this covariance set. And the sign function splits covariance for colors for positive crossings and colors for negative crossings, which I denote as C plus, C minus. Next, we have incident maps, which connects colors set for crossings and colors set for arcs. We have 4 incidence maps, and when we define good colors of diagrams of
when I look at polygon maps, it reminds me Nikonov differential graded algebra structure.
yes, maybe maybe there is a connection with the Nikonov algebra. So we have 4 incidence maps, and they are described by this picture. So if we have some crossings covered by C, then the colors of the incident arcs are defined from this color C and the incidence maps. And so we have 4 incidence map and have polygon maps.
Excuse me,
Yes.
Professor. What's the meaning of UDLR in the set?
Let us look at this picture. U means up, D down, up down, left and right. Up left, up right, down left, down right.
Okay.
So
Thank
we have
you.
four variants. Okay. Then we have polygon maps. The polygon maps described by sequence of these numbers. Epsilon means the signs of the crossings. So if we have a polygon, we have a crossing C0, C1, C2, and so on, and each of these crossings have some sign. So we say that C1 has sign epsilon 1 plus or minus, and other crossings have some signs which are denoted by epsilon. And then we have this parameter O, which has n elements in these parameters, and these parameters describe the orientation of the edges of the polygon. So by default, we assume that we have counterclockwise counterclockwise direction on the polygon, and each edge may be coincide with this counterclockwise rotation, or or be in the opposite. So we have some orientation for each edge of the polygon. This is another set of parameters. So we say that the edge is oriented counterclockwise if it in this case, if the edge oriented counterclockwise, we look the arrow, right arrow, and if the edge oriented clockwise, we will draw left arrow. So we have several parameters. So we consider polygons with the signs of the crossings and orientation of the edges. And each combination gives some map which defines the color of the crossing C0. C0. And we also assume that there is some compatibility relations which described by these qualities, and this equality just means that if we have so we have some the incidence maps, and these maps means that we have colors of the edges of the polygon, maybe A0, A1, A2. So, for example, if we consider the color of this edge, this color is defined by the incidence map from the colors of C1 and C2. And we say that this incident colors of the edge must be the same. So we have some relation that the colors of the edges in the polygon are well defined. And this gives us some restrictions by these equalities. So on the set of compatible colors of the crossings, C1, C2, and so on, we will have this polygon map. And for one gone or loop, we have a map from the colors for arcs to the colors of crossing. And in this case, we have the following picture. So we have one gone loop. We have some color of this edge, and this color determines the color of the crossing C0. So we have these maps, the structure, and then we should write down the relations between this incidence map, polygon maps, and the sign map. And the set of relations can be split it in several categories. First, we have polygon incidence relations. Polygon incidence relations, which means that polygon incidence these relations. So we say that the colors of edges and crossings in the polygon are compatible. Another set of relations, rotation relations. Rotation relations means the following: that assume we have a region, it is an n-gon, then we can choose any crossings and express its color through the colors of the other vertices. But we can take, instead of C0, the crossing C1, and this color of these crossings are also expressed through colors of all the other crossings. And we say that in this, so we have two different relations, and we say that they are compatible. So if, for example, if we express C1 through C0, C2, C3, and so on, and then we take this value and push it in the formula for which expresses C0 through C1, C2, and Cn-1, then we should get C0. So there is relations which concerns to changing of the vertex in the the region which we express through the other vertices. And then we have a number of relations which comes from right-dimensional moves, two relations for the first move, for the second move, and one for the third move. For the first right-dimensional move, we have two possible configurations when we make a loop inside the polygon or outside. So we have two different pictures, and here we write that the color of the vertex C0 are expressed in the left diagram, and in the right diagram are the same. These colors coincide. So these two moves, and for the second right-dimensional moves, we also have inner second right-dimensional move, which splits the polygon into parts, and an outer, where we from n-gon get n+2 gon by using this outer arc. And for the third right-dimensional move, we have the following configuration. And we may write down some relation for this three move. So we have some number of relations, and if these maps satisfy this relation, we say that we have a crossoid. Crossoid, and given a crossoid, we may define covariance of diagrams.
Can you state that some previously known invariants are partial cases of your crossoid invariants?
Partial cases. Below I will give some examples of crossoid, and so given a crossoid, we may consider the covariance of diagrams by this crossoid, and the number of covariance will be an invariant, and a special case of crossoids comes from biquandle or quandle. So the quandle covering invariance is a special case of covering invariance of crossoid. So given a crossoid, then we may consider covariance of crossings and arcs of a diagram by elements of this crossoid, which satisfy these incidence relations and polygon relations, and then the set of the number of this currency is an invariant due to these relations, which comes from randomized moves. So we have this crossoid structure, and sometimes it is a remark that using this inner second randomized move, we can split any region into small parts, namely into a triangle or bigons. And this means that when we define a polygon relation, we may restrict ourselves to the case of loops, bigons, and triangle. And this gives us another form of another definition of crossoid structure, reduced definition. So crossoid alternative in other way can be defined by using the sign map, the incidence maps, and instead of sequence of polygon maps, we consider only loop maps for one gons, bigon maps for two gons, and triangle maps for triangles, three gons. So we may consider these maps, and then using this inner omega-2 move, we can construct any polygon map expressed through these maps for loop and bigons and triangles. So we can define a crossoid using this loop, bigon, and triangle maps. Now here you can see the corresponding pictures. So we have 4 variants for the loop maps because there are 4 types of loop, and we have 6 maps for bigons, 2 maps for non-alternative bigons, which appears in second randomized moves, and 4 maps for alternative bigons. And we may take only 8 variants for triangle maps. So consider the following configurations, and each configuration, in each configuration, the polygon map gives some map, which is this case will be triangle map. So using this 4 plus 6 plus 8 maps, we can construct any polygon maps. And in the reduced crossoid relation, we should write down the relation between these maps, and the set of relation will have the following form: relation with the sign, some incidence relations concerning the
Or what does it mean
randomized.
reduced? Do you mean that they follow from something? That something follows from something else?
Yes, we have the original definition of crossoid. But when we restrict this definition for the case when we consider not all polygons, but only loops, bigons, and triangles, we get some reduced definition. And in fact, reduced definition and the original definition are equivalent. So they are just two forms to describe the crossoid structure. In some cases, so in some cases, it is more convenient to define polygon maps only for small polygons, such as loops, bigons, and triangles. And in this, when we use only 1, 2, 3 gons, the set of relations will be the follows. We have some relations concerning randomized moves and some rotation relations. applied to bigons and triangles, and flip relation. So you see the configuration for the flip relation. So we consider a square with the 4 crossings, 3 positive, 1 negative, and then we can use second master move to split this square into 2 triangles and 1 bigon. And we may use this triangle and bigon maps to express the color of this negative crossing. And the flip relation says that the result, the color of the negative crossing in the left picture and the right picture will be the same. Will be the same. This means that when we reduce the polygon map for the square to the triangle maps, it doesn't matter which how we reduce it with second master move. And then we can use these flip relations to say that the polygon maps is uniquely restored from these triangle maps and bigon maps. Because given a polygon, we can split it into triangles. We can code the splitting of this polygon into triangles by triangulation of the polygon. So we have a polygon where we have the distinguished vertex. Then we consider the dual polygon where vertices corresponds to edges and edges to vertices, and consider the triangulation of the dual polygon. And these triangulations corresponds to reducing the splitting of the polygon by second radicalized moves into triangles. And since any 2 triangulations are connected by a sequence of flips, then the flip relation is enough to show that the polygon maps is well defined, is uniquely restored from triangle maps. So we may use this to define a crossoid. We may use only polygon maps for one-gons, bigons, and triangles. And now let us pass to examples of crossoid structures. The first one is parity crossoid. We take any group G and consider G times -1, 1. And in this case, the set of colors for arcs is trivial. So we have only colors of crosses. In this case, the incidence maps are also trivial. The sign map is just we assign, we take the second component of the pair, G epsilon, and the polygon maps are given by some product of the colors of the vertices in some power, which depends on the orientation of the edges and on the side. So we have the incidence index, which is equal to 1 if we have pictures like this. Now we have a crossing here, our region, and here the orientation of the incident edges inside. And if we have a following picture, then the incidence index of this crossing is -1. So this formula gives us a crossoid structure. And if one consider coloring of a diagram using this crossoid, one get in this case we assign some color to each crossing, and this color is parity of the crossing. To be more precise, the oriented parity. So this crossoid gives the parities of the crossings of the node diagrams. And another example is biquandle crossoid. So if we have a biquandle, then given a crossing, given a crossing, we have two colors of edges incident to these crossings. I will take the right incident edges. So the pair of these colors, these elements of biquandle, which covers all the incident edges, describes the color of the crossing. So we say that the pair of colors X and Y is the color of the crossing, XY, and the sign of the crossing. So in this case, we have this description of color of crossing by elements of biquandle, and then we can write down the incident maps. So the incident maps are just induced just application of the biquandle operations to the colors, and then then we should define the polygon maps, and we can write down the following formula for the polygon map. It depends on the size of the crossing and orientation of the incident edges, and in this case the result are expressed using the biquandle operations, and so we have this form for the polygon maps, and one can check that this is a crossoid. And if we consider the colourings of a diagram by this crossoid, they are just colourings of the diagram by biquandle. So there is a bijection between colourings by biquandle and crossoid induced by this biquandle. So we have so thus the crossoid generalize on one side the parities of on nodes, on the other side biquandles.
Igor, you know that Denis, Ilyutka, and myself, we at some point we generalized the approach by Sam Nelson and generalized it in the way that both biquandle colorings and biquandle and some coloring enhancements of invariants and the parity bracket were both partial cases of our enhancements. So we had both parity bracket and quandle enhancements. So your crossoid is also a generalization of parity and biquandles. So just compare. This was something like 2019, maybe 2018, my work with Denis Ilyutko.
Okay, we'll walk through this. Okay, so
Also
we
look
have
at Nelson. Also look at Nelson's work. Sam Nelson.
Okay. So we have the following example, and in the case of Quandle, there is a theorem that currents of diagram, not diagram by Quandle, comes from Quandle homomorphism from some universal Quandle to the given Quandle. And in the case of crossoid, we have an analogous theorem. There is some universal crossoid, which is described using these homotopy classes of path which describes crossings. So assume we have a node in some thinking of some surface F. No, we can think that F, for example, is sphere. Maybe not sphere, the sphere. So consider a node. Then we consider homotopy classes of path, which comes from top to bottom and intersects the node twice, and the arc between two intersection points is framed. It's framed. So we may consider a tubular neighborhood of the node, and in this case, we can split this path into three arcs: under arc, middle arc, and over arc. And intersection points gives also two meridians of on the tubular neighborhood. So we have the following path. Then we may use this path gamma and mu to define some crossoid structure on the set of this homotopy equivalence path. So if we have a crossing, a diagram which is projection of some node, we can assign a so-called vertical crossing probe. So we call this path probes of crossing probes. And given a crossing, we have the following vertical path. And if we look at the framing of the middle arc, then we use the following rule to define the framing. So if we have a positive crossing and negative crossing, we connect this incident arcs by a band, and then say that this band defines the framing of the middle path. So there is some rule to define the framing for the vertical crossing probe. And then given our set of homotopy classes of these probes, we define the crossoid structure on this set. So we use define the incident maps for positive crossing, negative crossing, using this under, middle, and over.
Am I right that using this approach, you can define a crossoid for any for a node in any three manifolds without any projection to a plane?
No. In my paper, I consider only thickening of surfaces. But maybe I think we may use these formulas for any manifold. By we should say what is top boundary surface and bottom boundary.
But assume you have a manifold without boundary. Does your level of abstraction, a topological abstraction, allow one to define what is a crossing just topologically without referring to any projection and any structure like product or projection, just you have a knot in a three manifold. Do you have a definition of a crossing just topologically?
Yes, we can just write down the same, consider the same objects for nodes in any manifold. We just should check where to start, the point to start and the point to end. And if we take 2 points outside the node and fit them, then we consider this crossing probe and say that isotopy classes of these probes are crossings of our node. So we consider these isotopic classes.
Okay.
Formally, we can consider this sets in any manifold. But the question is how adequate will be this definition to say that this is a crossing. So we define the incidence map, then we should define loop maps, bigon maps, and triangle maps. And we use this picture. It is a projection from the side view on our node. So we have node, which is just a tubular neighborhood. We have top, boundary, bottom, and in this case, we consider this path with the following framing, and this path will be the loops, the corresponding loops, which corresponds to the arc. And then, then we define bigon maps somehow, also using the side views, and triangle maps. And then we get some formulas for bigon maps and triangle maps. So you can look at this formula in the archive paper. Okay. So these all maps will give us crossoid structure, which is called topological crossoid of the node. Topological crossoid of the node. And in special case, when we consider the unknode, this topological crossoid will be this product of integer number by 0, 1 by minus plus 1.
How does the crossoid behave with respect to the change of the orientation? So it's known that Quandle does not detect the double involution. What about the crossoid?
I think it also doesn't detect the double involution because
so you cannot so a priori you cannot detect between the right trefoil and the left trefoil, right?
Maybe I didn't check.
Okay.
So for the unknot, we have the following formulas for the topological crossoid, and there is also variant when we forget about the framing here in the middle part, and if we forget about framing, we will get some what is called unframed topological crossoid. And in general, we say that a crossoid is unframed if these two maps for two bigon maps coincide. I recall that in the case of non-alternated bigons, we have two types of maps. if we have a crossing, we have a weak map, a weak non-alternating bigone, and a strong non-alternating bigone. And if these two maps coincide, we say that the crossoid is unframed. And in fact, the parity crossoid and biquandle crossoid are unframed crossoids. So unframed, they're unframed, and the main theorem is that if we have a crossoid, a tangle in some surface in the crossoid, then there is a bijection between currents by this crossoid and the set of homomorphism from the topological crossoid to this crossoid, but but we consider only invariant crossoids, invariant homomorphism up to action of the fundamental group of the surface F. And in special case, when F is sphere or a plane, in classical case, so we may omit this action, it is trivial. So we have bijection between currents and homomorphism from the topological crossoid. And there is a variant for this theorem for unframed crossoids. If we have an unframed crossoid, that there is a bijection between currents by this crossoid and homomorphism from unframed topological crossoid. So this topological crossoid is the analog of the not quantum, but in this case.
Okay.
And we may define so then the num if we have a finite crossoid, then the number of currents is an invariant, but we may also consider an enhancement of this invariant cocycle of crossoid. We should take some abelian group and consider maps from the covers to these groups, and we impose some relations on this map. And if some relations, if these relations are satisfied, then we may define the cocycle invariant. For example, if we have the parity crossoid, then the map, which just a product of the if we have just the product of a group element and the sign of the crossing is a crossoid cocycle. And for biquandle crossoid, any biquandle to cocycle induces cocycle of the crossoid. And given a cocycle, one can consider this formula, cocycle invariant. Cocycle invariant, it is an analog of quandle cocycle invariant or biquandle cocycle invariant. And one can see that this is a tangle invariant, not invariant. In special cases, when we take parity crossoid, this formula gives the index polynomial. And for biquandle crossoid, this is the biquandle cocycle invariant. And in fact, this cocycle can be included in more general construction of crossoid homology, analogous to the case of quandle. By quandle, we may define some complex, and this cocycle is just a cocycle of this complex. So there is some formula for the differential. And in fact, this differential has some geometrical meaning. We should consider the following configuration of n arcs, and they form a polygon, a sequence of crossings. And then we take any arc I and move it to the bottom, down, or up. And we have two different configuration, and using the polygon maps, we can express the chaos of the new crossings through chaos of the old crossings, and this sequence will be the differential. So we take this sequence of these crossings minus sequence of these crossings, and the sum for all I, for the arcs I, and this will give us differential. This will give us some cubic object or semi-cubic object, and the corresponding differential. And crossoid cocycle is just a cocycle in this complex. So we have an analog of cocycle invariant for crossoids. And if we look at the homology of this crossoid homology, in the case of biquandle, we get the biquandle homology. And in the case of parity, it appears that the differential is 0. So the homology coincides with the chains. So chains is just a free group on the complement. We should remove the unit of the group of the parity crossoid and multiply it somehow, so we get this formula. And this means that the cocycle invariance, which corresponds to the case when n equal to 2, takes values in this free group of G generated by the elements of G except the unit. Except the unit. So here you can see some references, and the material I talked just now you can be found in this paper. So that's all what I wanted to say. Thank you for your attention. Are there any questions or comments?
Are there any questions or comments, remarks? Okay, if it's not the case, so thank you very much for the attention.